Let me start the recording here. Oh, all right. As we move forward on this last topic of lasers, then, where do we start? So here's what I want to remind you guys of from earlier in the course. Remember that there are three primary ways that matter interacts with light. And they're called spontaneous emission, absorption, and stimulated emission. So brief review or explanation. Spontaneous emission is when we have an excited atom or molecule, excited, either it's the whole thing is vibrating or rotating, or here we're showing the electron being excited in a cartoon form. And spontaneous emission is at some point the electron decides to lose that energy and give it off as light, and it gives it off as a photon in a random direction. Here I'm showing all the photons going to the right, but this process, there's equal probability for emission at any angle in spontaneous emission. Absorption is, of course, the reverse of that process, where a photon comes in and excites a molecule to a higher energy level, either a higher electron energy level or higher vibrational or rotational energy level, but it's the inverse of spontaneous emission. The process that's important for us today and in the remainder of the course is this third one that we didn't talk about much, called stimulated emission. And this is where we have an excited atom or molecule or electron, and a photon comes in and perturbs that state. When that happens, that photon, that incident photon, can induce the electron, or whatever our system is, to give off its energy as another photon of the same frequency with the same wave vector, so in the same direction. And of course, we need to have the energy levels aligned, so a photon being given off at that frequency is possible, but assuming all of that is the case, we can get this process called stimulated emission going. We just need to have a photon of the right frequency in the right direction. So this is what we're going to talk about this week, and how we can use this to amplify light. So if we want to use this process to amplify light, what we really have to do is take a photon, so the blue photon shown here, and send it through a medium where all of the atoms or molecules are excited in some way, and have an energy level transition equal to the energy of this photon. If that happens, if we have that case set up, what happens is this: the photon enters the material and will interact with the excited atom, molecule, or electron, and induce a transition to create a second photon, which will then, and this process happens over and over and over again, we get this doubling cascading effect, where one photon becomes two, two becomes four, four become eight, so on and so forth. So if we want to amplify light using this process, our goal is to take a small number of photons, send them through a medium with energy levels at the right positions that will allow this photon to induce the electrons to emit you could say like carbon copy photons with the same frequency in the same direction. And there's several ways you can do this. One, you could obviously have a really long and large excited medium. That's usually not the way this is done, though. The other way you could do this is have this process happen one or two times, and then place a mirror at one end of the excited medium to cause all that light to go backwards, and repeat the process again. And throughout this whole process, you of course have to keep throwing energy into the medium somehow. Every time an electron drops to a lower energy level, if you want this process to continue indefinitely, you have to somehow throw energy back in to get all those electrons back up to the higher energy levels again. So in order to get this process to work, we're going to need some way to get energy into an excited medium. We need what we call the excitation or gain medium. We need a way to direct the light on a repeating path through the medium. And we need a way to keep throwing energy into the medium. So as we go along, I'll keep making this picture a little bit less cartoony and more detailed as we get into more details. But basically, this is the essence of a laser. The overall factor, so the key figure of merit or number of merit, if you will here, how we characterize a laser is this thing called the gain. So this is the factor by which an input beam is amplified. And it's usually written in terms of the intensity. So the gain is the ratio of the intensity of the light before we went into the gain medium, and then to the ratio, so the intensity of the light after the gain medium, the ratio of the intensity of light after the gain medium to before the gain medium, that ratio gives us the gain. So it's the ratio of how much your intensity increases. It was a little bit convoluted there. That makes sense to everyone? Any questions? Okay. So let's see just like the basic idea of how we can get this to work. So we're not going to care just yet how we get energy into the gain medium. So how we get all those electrons up to their higher energy levels, so they have all this energy they can give away. We'll worry about that later. But let's say we have that working. In order to set up this process, we could do something like so. So we could take our excited laser material with the excited electrons and put it between two mirrors. One mirror is called the high reflector, and it has a reflection of 100%. It's perfect, or as close as we can get to a perfect mirror, hence the name high reflector. The other mirror is called the output coupler, and this has a reflection that's less than 100%. Might be 90%. So basically the idea is this. We have some lights, we have to hit the medium with some light source, which is then amplified, travels through the gain medium and gets amplified, and it's a little bit stronger, but not quite what we would expect. Yeah, or not quite what we want. So some of the light hits the output coupler, a little bit gets out, but most is reflected back. Travels through the gain medium again and is amplified. So I0 becomes I1, hits the mirror, becomes I2 after some escape, I2 becomes I3, is all reflected back into the gain medium, becomes I4. All of these intensities keep getting bigger and bigger the more times you pass through the laser medium, until the intensity gets so high that we just can't keep up with the amount of energy we're throwing into the medium. So eventually there's a limit you hit, you get to a steady state, and eventually the 10% of light gets out, is still really, really strong, and in a very tightly focused beam, because all of those photons have the same wave vector. And of course, as they get out through these mirrors, which are usually spherical, the beam is not perfectly, the beam still does spread out somewhat due to diffraction. So you don't get a perfectly tight beam that doesn't spread out, but it's pretty damn good compared to what we see with other light sources. So here's what we need. So if we want to, one, we're going to define a new verb here, the verb to laze, meaning to amplify a beam of light in the method shown. It's kind of one of those words we just make up for physics. And so basically what we want to say is that the laser will laze or amplify light as long as the intensity increases during one round trip. So we want I3 to be bigger than I1, I0. What goes into this? So we have to remember that, of course, there's going to be losses in the material. Some of the photons that travel through the gain medium will be amplified, but others are going to be absorbed by atoms and cause things to heat up. So usually there are losses in there as well. So in general, we could get this process to work as long as we could get a medium where the total gain is greater than the total loss. And in laser terminology, this is called achieving threshold or lasing threshold. Hopefully just, this is something that if you're a physics major or whatnot, should be pretty straightforward from just kind of an overall conservation of energy argument here. So another term for this would be laser oscillation, because the light kind of bounces back and forth between the mirrors like a simple harmonic oscillator. So our goal is to now describe this mathematically. And we can do that by setting up some first order differential equations. This was first kind of the coefficients. These differential equations are going to involve things called A and B coefficients that were originally thought up by Einstein. And they are coefficients that approximate the rates of absorption, spontaneous emission, and stimulated emission. So we're going to define a few here. So the rate of, the way these are going to be defined, the absorption rate is going to be the amount of photons per second that are absorbed by a material. So there's going to be some constant B times the number of molecules you have in the lowest energy state. So here we're going to consider, if you look up in the overright, just something with 2 energy levels. So some simple material just with 2 energy levels that are working. So we will want the number of atoms or molecules in the lower energy level state and the intensity of the light. Both of these things are proportional to the absorption rate. The more photons we have, meaning the higher the intensity, the bigger absorption we have. The more atoms in the ground state that we have, the more atoms are going to be able to absorb. The more photons the atoms will be able to absorb. So the absorption rate is proportional to both of these things, and the constant proportionality is B. Similarly, the rate of spontaneous emission, atoms just randomly giving off electrons or giving off photons in any random direction, is going to be proportional to how many atoms or molecules we have in the higher energy level 2. The more that are there, the more it can give off energy as light. Constant proportionality there is called A. And this is the key thing. So the stimulated emission rate is also proportional to the intensity I and the number of atoms in the higher energy level. However, the key thing to notice here is that the constant of proportionality is the same as for absorption. I'm not going to get into why, because that's a very kind of high level quantum mechanics calculation, way beyond the scope of this course. But from a physical perspective, hopefully it's not, hopefully it's physically reasonable. Stimulated emission involves kind of an atom being perturbed, or an electron being perturbed by a photon. So there's kind of there's still involved here, you have an excited atom or molecule or electron interacting with a photon for a brief amount of time, whereas with absorption, it's kind of absorbing it permanently. So it's physically reasonable that the same constant would appear in both of these rates. Okay, any questions about defining this terminology? All right. If not, then we can use these to set up some differential equations that describe the process, these different processes, and how they all are involved in the workings of a laser. So first, let's try to compute the laser gain, or get a formula for the laser gain. So here we're going to neglect spontaneous emission for now, and consider just absorption and stimulated emission. So if we want to consider the total gain, we want to consider how the intensity changes as the light propagates along the z-axis through our material. So here, that's going to be proportional to our total stimulated emission minus our total absorption. So the absorption here can be in part our loss. So you'll see the total constants are the same. The initial intensity of the light is the same. So we can see that the rate of change of the intensity versus travel distance through the lasing medium is proportional to the difference in the populations of the two energy levels. So if, for instance, here you could see if we have more excited atoms than we have atoms in the ground state, our intensity of our light will grow. If, however, more of the atoms are in the lower state, we're going to have more absorption than we have stimulated emission, and the intensity of light will decrease. So fairly physically reasonable. If we solve this equation, you can look at it and see this is a first order differential equation for an exponential function. The constant proportionality appears in the exponent here is sigma. And this is called the absorption or gain cross section. It has a weird name because it comes out with units of, if you do like a 3-dimensional problem, units of area. So why it's called a cross section, but really it's just a constant proportionality that tells you more or less how much your lasing medium is interacting with light. So we could use this to define our gain. So we see that the gain is one exponential, and the gain is if the higher energy level has less atoms in it, then we really get a loss. But if our higher energy level has more atoms or molecules in that state, then we can get a gain and define it for N2 greater than N1. And what is, oh, there we go. Sorry, it looks like one of my, give me 1 second here. Looks like one of my equations here is really tiny. So I don't know how that happened, but what is going on? Sorry about this. There we go. All right, so our gain is our, still a little stretched out, but now at least you can read it. Our definition of the gain in the laser is given by this exponential. So if we want to find the gain for traveling through the entire laser medium of length L, it's this quantity where we let Z equal L. Often this quantity, sigma times N2 minus N1, we just write that as G. That's called the gain coefficient. The entire gain, the gain itself is capital G, the exponential. The gain coefficient is all this other stuff inside the exponential minus the distance. If N2 is less than N1, so if this coefficient is negative, it's called the absorption coefficient instead. And using notation from earlier in the course, we use alpha. Is that clear to everyone? Any questions on how any of this is being defined or the physics behind it? Okay, good. So we can see just using some like proportionality relationships here and some fairly simple models for absorption and emission that we can get fairly straightforward definition of how much the light is being amplified if we can set this up properly. So if you want to look at this in another way, basically what it says is that in order to get a positive coefficient in that exponent, and thus in order to get the intensity to increase with travel distance, what we need is to have more of our atoms or our molecules in the higher energy level than the lower energy level. And in laser terminology, this is called population inversion. Normally, as you guys know, everything wants to hang out in the lowest energy level possible. But in order to get a laser to work, you need to set up a situation where the reverse is happening, where you have more atoms or molecules in the higher energy level state. So again, called inversion, it's inherently non-equilibrium. It's something that you need to set up. It's not, nature doesn't want to set up this way. It's something you have to force it to do. And that's why we need to keep throwing all this extra energy into our laser to cause this gain effect. And so really, if you want to see something like this, in thermodynamics theory, this is often called a state of negative temperature, but you may hear that later going on. It's more of a mathematical thing. It's not really that the temperature is negative. But here you might see the case where this would be an example of population inversion. It depends on what two states you're talking about. So for here, if we're sending in a photon into this material with all of these energy levels, and we want to cause stimulated emission between energy level 4 and energy level 2, this would be a case where we have inversion. 3 atoms or molecules in state 4, only 1 in state 2. There is not inversion between 4 and 1 because they have equal populations. But if we're not using the transition between those two levels, then that's not a problem. The key thing we need is population inversion between the two levels that are important for the photons we're trying to amplify. So you can kind of say this is that we have to hit this laser medium very hard with some type of energy source. And we also have to choose our lasing material correctly so that it has the right energy levels, it's transparent to light, and we can get it accepts all this energy that we're giving it. So depending on what type of photons you want to amplify, the material is different. One of the first ways this was done was more or less by using an external light source, a really, really bright lamp, to pump energy into the lasing material. This is a very kind of cartoony way to picture that, of course, but this is generally how it works. That initial flash from those external light bulbs causes a lot of electrons in the laser medium, or a lot of the atoms and molecules, to jump up into the higher energy level, which gives us the population inversion that we need. You can also do this electronically or electrically by, for instance, putting a voltage across the material, a very high voltage. That's possible with what we call laser diodes. So there are multiple different ways that you can do this, but this would kind of be one of the first ways. In a helium neon gas laser, like the ones we were using in lab, the population inversion is accomplished by putting a high voltage on the order of like 1500 volts across a vacuum tube of a mixture of helium and neon gas. So this outside energy source is what gives us population inversion. And as this population inversion happens, and then photons are amplified, the populations of the two different energy levels in our problem are going to change. And in order to, the equations that describe this are very important for describing how well a laser is going to work. So my main goal for the rest of the class here is to discuss some of these equations. They're called mathematically rate equations. Again, they're first order equations, differential equations, and similar to a lot of equations that describe chemical reactions and the rates of reactions in chemistry. That's where the name comes from. So for here, for instance, we want to look at this, we're going to look at this problem a little bit more in depth now. We want to figure out how the populations of these, or the number of atoms or molecules in the different energy levels, are changing with time. So for instance here, we could look at the rate of change of the number of atoms in the higher energy level, dN2 dt. So this is going to be proportional to a few things. The absorption, so how many electrons from the ground state or atoms from the ground state are absorbing photons and jumping up to the higher state. How many are being stimulated to lose their energy and jump back down to the lower state? And of course, we're also, throughout this whole process, also going to have spontaneous emission. So some of our higher energy electrons or atoms are going to give off energy on their own without being perturbed by photons. And in fact, that's usually how we get the initial photon that we want to amplify. Basically, you excite your material, and initially all you have is spontaneous emission. Photons going out in all directions, just randomly whenever the atoms want to lose their energy. And then, from there, one of those photons randomly will eventually have the right wave vector to hit the mirror dead on and be reflected back into the material, in which case you then start stimulated emission. So spontaneous emission is where we get that first photon that we then amplify with stimulated emission. And here, all of these quantities are going to be proportional to the intensity of what we call our pump beam, meaning the beam or the light source that is pumping all the energy into the system. So that I sub P is the, if you want to think of it, the energy of that flash lamp, or it might be another laser that we're hitting, as in the photograph on the first slide. Or that might be, IP might be something related to our voltage in our helium neon laser. Here I'm going to work with this example of it being a flash bulb or some external light source. And B and A are the Einstein rate coefficients that we defined earlier. We can do the same thing for the rate of change of the ground state, N1. So the only thing that changes here is the sign on this first term. Well, the sign on both terms, actually. So these two, dN2 dt and dN1 dt, since we only have two energy levels in this problem, should be equal, but with opposite signs. So we now want to see if we have a total number of molecules n, n1 plus n2 must equal n. And then we'll call delta n the difference in populations of the two energy levels. So we can combine these two equations to get an equation for delta n. So d delta n dt looks like so. And again, it's just subtracting these two, taking dn1 dt minus dn2 dt to get d delta n dt. And we could rewrite n1 and n2 all in terms of n and delta n. So the end goal here is what we're getting is a differential equation for how the population inversion is changing. And you don't have to copy down every line here if you're taking notes, but here's just kind of a lot of algebra to get things just into the terms of the variable we care about, delta n. And once we do that, we have this equation. So remember, the total number of atoms and molecules n is a constant. So we have the rate of change of delta n is given by really these three terms. First thing we can look at is the steady state case. So we are throwing all this energy into our lasing material, and eventually it's going to start giving off light either through spontaneous or stimulated emission, and eventually that'll eventually hit a point where that's balanced by the absorption in the medium and all the energy we're throwing into it. If we wanted to figure out what delta n will be in that steady state case, then all we have to do is set the derivative equal to 0 and solve for delta n. And when we do that, you can kind of simplify directly and see that delta n is going to be proportional to the total number of molecules that you have the total number of molecules in the medium that are actively interacting with the light, and divided by this denominator where we have the intensity of our pump light source divided by this quantity, our two coefficient, the ratio of our the absorption coefficient to the emission coefficient, A divided by B. That has units of intensity, and it's called the saturation intensity. And it's a really important quantity for determining whether a laser can possibly work. And here's the issue here, though. With this one tiny problem with the two-state system, is that if you look at this equation, knowing nothing else, delta n is always positive. So what that means, remember the definition of delta n here. Delta n was defined as the ground state, number of atoms in the ground state, minus the number of atoms in the excited state. So this means if you just have a two-state system, you can never get a case, no matter how much energy you throw at the material, you'll never really get to a case where you have population inversion. The atoms just end up falling back down to the ground state too quickly. So if you only have a two-state system, you can't get it to work as a laser. So that's why I say inversion here, population inversion, and thus lasing is impossible if you only have a two-state system. Really what you need at least one more state in there, and ideally two more. And I'm going to try to show you why conceptually on the next few slides. I know there's a lot of algebra here, so before I move on though, the algebra really isn't all that important in the end. Do you guys see any questions on seeing this conclusion I'm drawing? That delta n has to always be positive, which means there's no absorption. I encourage you to go back later once the slides are posted and follow your way through the algebra just to make sure, check my work. But hopefully it's clear. We're looking at a steady state condition. So we're setting the derivative equal to 0 and solving for what the difference in populations for our two levels will be. Basically, once we turn everything on, let it heat up and let it hit an equilibrium. Okay, good. So if we only have two states, we can never get the system set up in such a way so that we can get lasing. So let's see how adding in a third or a fourth state allows us to get population inversion. So here, for instance, let's look at a case, let's put a third state right above the second state we had before. So we have our kind of color coding scheme here. We have photons coming in from our flash bulb or our external energy source that knock electrons from the ground state up to state 3. That is our, what we call the pump transition. But then, state 3 is what we would call a very unstable state. Electrons don't like to stay there, or the atoms or molecules, whatever. And they decay to a lower state, state 2, that is what we call metastable. It means the time to decay back to the ground state is really, really long. So they can hang out in state 2 for a long time. And it kind of forms a bottleneck there. And eventually this type of process conceptually quickly jump up to state 3, knocked up to state 3, quickly fall back down to state 2, and then hang out there for a bit. That allows us to build up a population inversion between states 2 and 1. So this is the type of system that we need to get a population inversion. So again, what we're going to do here, basically level 3 decays so quickly that we're going to assume that its population is always 0. But the fact that it's there is important, because the fact that that state 3 is there is that it eliminates the fact that our pump light source is affecting the process overall. So it allows the frequency at which we will laze to be different than the frequency in which we're using to throw energy into the system. And that's the key thing that makes the difference. So again, just kind of working at the end here for the, we have to go through the same process of finding the differential equation for d delta n dt, and then rewriting the whole right-hand side in terms of delta n. It's the same process it was before. The only difference here is that now we are missing the stimulated emission term in this equation. And that's going to allow us to get a case where delta n, where n2 can be bigger than n1, and thus delta n can be negative, and we have population inversion. So again, for the sake, since going through all this is not the most fun online, let me just take you to the end of the algebra. And if you want, after class, I'm happy to go through this with you guys if you have questions about the math. At the end of the algebra, we end up defining this constant A divided by B, which is units of intensity again. We're going to call it still again the saturation intensity. But now it looks different because that saturation intensity and that ratio of the pump intensity to the saturation intensity now appears in the numerator as well as the denominator. So you can see here that delta n might not always be negative, but if we hit this thing with enough energy, if we make our pump intensity big enough, eventually this term here becomes bigger than 1, which makes delta n negative, which means that there will come a point where the atoms and molecules in state 2 will be more than in state 1. And that gives us population inversion. So this is a state where if we can set this up, if we had a material with energy levels like this, and they are out there and they exist, we could conceivably use this material as the gain medium in a laser. But you need to have at least 3 states you can work with, and one of them needs to have this property that it decays really quickly to a state kind of just below it. And the other one needs to have a slower decay. Those are things you, of course, can predict with really advanced quantum mechanics. We're just going to take it on faith that energy levels like that exist. And the timing of how fast these states decay is something that we know and have tabulated. So if you have a 3-level system, then what you have is, sorry, give me 1 second here, guys. I don't know if that affected you, but there was a truck outside that was quite noisy. But the takeaway message here is that if you have this 3-state system like this, lasing is possible. And in fact, we can even make it easier by adding in a 4th state. So the 4th state here, basically what we want is a state below what we were before calling our ground state. So if we add in if instead of having our lowest state be the ground state, it was one just above the ground state, we could do something like this, where our pump can knock our atoms or molecules from the ground state up until state 3. And then state 3 decays really fast, and then we get to all of our atoms and molecules building up in state 2, and they hang out there for a while. And then we could use the transition from state 2 to state 1 to be the transition we use to build the laser, to do stimulated emission to amplify our light. If state 1 has a fast decay back to the ground state, what that essentially will ensure is that the population of state 1 is approximately always 0. As soon as a stimulated emission causes an an atom to decay from state 2 to state 1 and give off a photon. That atom that's here immediately then jumps down to the ground state. Doesn't hang out there for long. That ensures that N1 in our rate equations is always 0, which will ensure that N2, no matter what it is always greater than N1, and we always have population inversion. So if you can get a 4-level system like this, set up with these properties of the decay rates between the different states, not only is lasing possible, but it's actually, relatively speaking to the other cases, particularly easy, because you always have population inversion. So since N1 is always 0, again, I'm going to jump down to the end of the algebra here. Delta N is just equal to minus N2. So if we want d delta N dt, we just have to take the negative of this guy. Again, going through algebra, redefining, setting the derivative equal to 0, solving for the steady state delta N, and defining A over B as the saturation intensity. I'm going to show you the end result here. What we get is delta N. Our population inversion looks like this. It's proportional to the total number of molecules you have in your system. But now this quantity is always negative, no matter what your pump intensity is, no matter how much energy you're throwing into this medium. If you're exciting atoms to higher energy levels, you will always build up a population inversion in level 2, between level 2 and 1. So notice here the coefficient out front just has a negative sign. And even if your pump intensity is less than this ratio A over B, the saturation intensity, this numerator is still always positive. So it means, because of this negative sign, that delta N, regardless of how much energy you're throwing into the medium, is always negative. There's always more atoms in state 2 than state 1. And you can always, in theory and in principle, no matter your pump intensity, get a situation where you can get stimulated emission between states 2 and 1, and get it such that you have enough energy and enough atoms in state 2 to actually amplify your light. The end goal for us here is really to use these kind of equations to predict delta N. Going through the algebra of the equations is not super important, but the end goal here is we want to now, if we want to build a laser, our goal is to find systems that have energy level transitions like this. And those systems can be solids, they could be gases or mixtures of gases, as long as there's some way to transfer, to get energy to jump, or atoms and molecules to jump these energy levels with these fast and slow decay rates. So the type of systems can be very different depending on what color you're trying to lase at. But generally, they're always 3 and most likely 4-level systems. And they're going through this type of process. So kind of to summarize really what I want you to take away from this lecture is the 4-level system is what we need. Lasing is easy. If you have a 3-level system where you have this fast decay in that top state, you can still lase, but it's harder, it's less efficient. And on class on Friday, we're going to talk about experimentally a lot of the systems, how like helium neon gas or different ruby crystal or diode lasers, where they fit in this model, and show you about where they lase. So this is going to be a very application-oriented section of the course. That's all the new stuff for today. If you guys are interested, I'm happy to hang out and go through some more of that algebra and math in detail. But if you guys got the basic idea of how these energy level systems, how these different types of energy level systems make lasing possible or easier or harder, then that's really what I want you to get from today's lecture. So we're done with new material for today. Thank you for listening, and See you Friday if there are no questions.